Good morning. Welcome back. We are in part 2 of time domain analysis of first order system. We know about whenever you hear first order system, this term should come into your mind, 1 by 1 plus st. So in this class, we are going to see the following contents. First order system with steady state gain, we'll see it in the end of this class. The major focus of this class is step response of an RC network. So you should know, like, let us, exam is important, but that is not everything. After learning control system, you should have a very clear understanding about what is step response. I have shown you the vessel example. Being electrical engineers, I'll show you an electrical example. Okay, so that is the agenda for today's class. Then you should know that always conducting experiments may not be easy. Like if you want to learn to ride a cycle, you can ride a cycle. Maybe you will fall. You may break your knees. You may have some minor accident. That's okay. You will learn by trying. Okay, on actual cycle. Okay. But if you want to learn how to control an aircraft, if you want to become a pilot, nobody will let you fly in the first chance, because if there is some mistake, the accidents will be fatal. You will die. Okay. So usually you will play the model. Okay. So one agenda for this class is not of examination point of view. One agenda for this class is to make you believe that you can get results experimentally, the same results you can get mathematically also. That is why we learned Laplace and inverse and differential equations. So we will get, let me repeat the agenda for today's classes. You will obtain a response experimentally, and then we will obtain the response analytically, that is using equations. So that is the main agenda of this class, and we will talk about systems with steady state gain also to make it complete. Okay, so that is the agenda. So let us consider a very simple system, our favorite RC network. So this you can hook up in the lab. So what is the agenda? We have to get step response of an RC network. In fact, you will do this experiment in the semester in control system lab. So you have a resistance, you have a capacitance, you can take a resistance, you can take a capacitance, connect it on the breadboard. You want to get step response. How will you get step response? You can, in fact, getting a step itself is difficult experimentally. You can take a function generator, apply a low frequency square wave. You know square wave. This is square wave. If it is low frequency square wave, then how will it be? This is the first high. Low frequency, it will remain high for a long time. Maybe after you sleep, it will go to low. So in the lab, you will get a square wave. You will get a step from a square wave. If the frequency is very low, say 10 hertz, then the time period will be 1 by 10, 100 milliseconds. So that is the idea. Okay. And how will you see the output? The output is, as shown here, is the voltage across the capacitance. So let us look that. Okay. So here there is a function generator. I'll put in square wave. I'll adjust the frequency to say 10 hertz. Then 10 hertz means 100 milliseconds. 100 milliseconds means this time will be how much? Will be 50 millisecond. So let us look at the physics of this. Let us forget about all the equation. When the voltage, this voltage is 1 volt. You apply 1 volt square wave, so this height is 1 volt. So when you give a 1 volt here, what happens? The capacitance will get charged. So that voltage across the capacitance, what will you know from the physics? The voltage across the capacitance will increase, isn't it? Will increase slowly. My drawing is not very good. The voltage across the capacitance will increase slowly and it will reach 1 volt. Once it becomes 1 volt, what will happen? The voltage here is 1 volt and voltage here also is 1 volt. So no current will flow and it will remain at 1 volt. That is the physics of it. And if you do this experiment in the lab, you will get the response. The voltage will slowly increase and it will reach 1 volt. And what is this time? You look at this time by the time when it has reached 1 volt. It has reached 1 volt roughly with 5 milliseconds. Yeah, I hope you remember in the last class I said about time constant, and for this system the time constant is 1 millisecond. So the response of the first order system has reached steady state within 5 milliseconds, or in terms of electrical engineering terms, the voltage across the capacitor has become 1 volt in 5 milliseconds. So this is the experimental result. Without going to the lab, we can obtain the response using equations. So being engineers, we should be good in equations. So I know that I have told you about this. We will get response mathematically. So how will we get response mathematically? We all know that we should get the transfer function of the system. Once we know the transfer function of the system, GFS, I can find RFS, GFS into RFS is CFS, take L inverse, I'll get CFT. So we'll do that. To get transfer function is important. You should write the equations for the system. So here the input voltage is, how much is the input voltage? R into IFT into R plus 1 by C integral IFT dt. So that is the input voltage. What is the output voltage? Output voltage is the voltage across this voltage. The voltage across this is how much? Is 1 by C integral IFT dt. This I am sure that all of you know it. So step 2 in finding transfer function is you take Laplace transform of both the equation. What is VIS? IFS into R plus IFS by CS. You know that when you integrate, you divide by S. I have taken the IFS outside. Then what is V0S? I have to integrate, I have to take Laplace transform of this equation. V0 of t is 1 by C integral IFT dt. The Laplace transform of this equation is V0 of S is equal to 1 by CS IFS. So I know V0S and VIS. What is transfer function? V0S by VIS, which is equal to 1 by CS divided by R plus 1 by CS. By doing simple algebra, you will get V0S by VIS is equal to 1 by 1 plus RCS. So this is the transfer function. So now the beauty is, the point which I want to drive in is, you have a system here. This system could be represented by this transfer function. The system, the RCA network could be, then you needn't go to the lab. So if you know the values of R and C, then you can get the response. You can get the transfer function and then you can get the response. So let us do that. This we have seen in the last slide. So 1 by 1 plus RCS, I will write it as 1 by 1 plus TS. So this is another conceptual point which I want to drive in. So we are going to learn about all first order system in the same way. let it be RC network, let it be thermometer, let it be anything, we'll represent it as by 1 plus Ts, and T is called the parameter of the system, and T is the time constant, okay. For RC network, it is R into C. So this kind of encapsulation, this kind of thinking is required. That is, let me digress a little bit. All of you know about periodic table. So I think I learned about periodic table when I was a kid, when I was say 8th or 9th standard. It's some more than 40 years back, I think. So I even now remember, I was so fascinated by mentally that you can study everything in a very systematic manner, okay. You needn't study different elements in a different way. You learn all first group element together, okay. Hydrogen. It's long back, okay, so I've forgotten. So one of my favorite group was the 7th group, okay, the most reactive group. Chlorine, bromine, iodine. So 7th group means every 7th group element has similar behavior. And the characteristic of the 7th group is you have 7 electrons in the valence shell. So the characteristic of first order system is this guy, this very important person, this very important parameter. So first order means you should know the time constant. So time constant is a physical quantity, okay. You should have a physical feel for the time constant. For this system, the time constant is R into C. So I have given some numbers here. R is 1 kilo ohm, C is 1 microfarad. So R into C will be what? 1 kilo into 1 micro. Kilo is 10 raised to 3 and micro is 10 raised to minus 6. So RC will be 1 millisecond. I think I have calculated it. So where T is RC, and we know. So that is, we needn't derive the response. We needn't find CFS is GFS into RFS, then inverse. Even in the form 1 by 1 plus Ts, response is 1 minus e power minus T by tau, or here I have written it as capital T. And what is capital T? It is 1 millisecond. So what does that mean? When you know the time constant is 1 millisecond, then you know many things about the system. You know that the system will reach steady state in 5 milliseconds. So knowing time constant is very important, okay, in real life also. I'll give you one a politically correct example, then I will give you for you to remember. Please excuse me, a politically incorrect example also. A politically correct example is, if you have a fever, slight headache, then what will you do? You may take a paracetamol. If you take paracetamol, how much time does it take for your headache to go? Maybe half an hour. Your headache won't go in 10 milliseconds, isn't it? So the headache, the time constant is 10 milliseconds. The action, the step input is you are taking a paracetamol, okay. So it is fast. Another example is you break your hand, okay. You go to an orthopedic surgeon, and usually you have this feeling of getting well within, we won't call it time constant. We think that, okay, God willing, I should be better in a couple of days, okay. So the orthopedic surgeon would not want to frighten you, so he'll say that it'll take a week or so, but he's just being nice to you. The time constant for an orthopedic problem, for bone healing, is months, if not years. So if you have an accident, then count it, it'll take 5 months to cure. So the time constant there is 1. So a politically incorrect example is with my sister, okay. When she was young, she thought by putting some particular oil on the head, your hair, you will get very long blonde hair, okay. So she applied it. She came out of the bathroom and started trying. My hair has not grown. So she didn't realize that The growth of hair, the time constant is uh, maybe months. Okay, it will take some time. Okay, and another last example. Maybe I'll tell that later on. Okay, so what is the response? The response is 1 minus e power t by 10 power minus 3. So without going to the lab, if you know the values of R and C, you can sketch the response. So you can, for t is equal to 0, you can compute this number, C of t, you will get 0. When t is equal to 1 millisecond, you will get 0.6321. This guy is very important. Why is this guy important? When t is equal to 1 time constant, your response will reach 63%. Okay, so you can, if you want to compute, find time constant of a system, you look how long it takes to reach 63% of the steady state value. So you can draw the graph. So this is exactly the same graph which you obtained from the lab. So I would recommend that you, when you are going to the lab, when you are doing the experiment, first you draw the graph and then go to the lab and then do the experiment. If you are getting the same, be happy and believe in control system and believe that we have to learn Laplace transformation. It is for good, not for headaches or not for difficulties. So let us complete the characterization of first order system. In general, we are interested, a general first order system will have two parameters. It will have a steady state gain also. There is a state here, steady state gain. So then it's not represented by k by 1 plus st. It is represented as 1 by 1 plus st. It's not represented as 1 by 1 plus st, it is represented as k by 1 plus st. So the response is just a scaling factor. The shape of the response will be same, only thing is that it will get multiplied by k. So the point is, if k is 2, then you give a step input, it get amplified. If k is 10, you give a step input, it get amplified by 10 times. So k is the steady state gain. Okay, so k is the steady state gain. If k is equal to 1, the steady state value will be of Ct will be equal to 1. If k is 10, steady state value of Ct is equal to 10. What is steady state value? I have shown that. I hope I can draw a graph. This is the step response. This is our time axis. Let me choose another color. This is my time axis. This is my time axis, and this is the steady state value. So if k is 1, the steady state value will be 1. If k is 10, the steady state value will be 10. So in summary, first order system is represented by two parameters, k and tau, or k and capital T. Better say tau. For typing capital T is easier. Okay. And response is k into 1 minus e power minus t by tau. K is steady state gain, that is the final gain for the system, and t is the time constant. I promised I want time constant to remain in your mind. Okay, so what is time constant? It tells you how fast the system responds. I told you the example of accident, headache. I'll give you one more example. Okay, like if you have a kid in your home, like a young kid, how long will be young kid? Maybe on the first day after delivery, it will be 1 foot. After 10 days, it will increase the length. She will become taller. By the time she is 1 year old, bigger. So you can see, if you plot the height of a kid as he grows, you'll see that by the time the kid reaches 18 years, it will reach the steady state. Okay, maybe she may be 5 feet 7 inches and will remain 5 feet 7 inches for a long time. Okay, That is about the kid. So the time constant there is years, okay, maybe 2 year, 3 year. So, but if you consider time constant, I'm not talking about first order system, hello, any system. If you take some plant, the plant, if you plant some normal plant, not botanist, I can't recall any plant. It will within few days it will increase the height, or if you have a kitten, it will grow faster. Okay, so that is the time constant. Okay, so that's all. Thank you very much. Hope you enjoyed the class. Okay, thank you.